Hello, it's Carter Collier. I'm going to be explaining homework 2 for heat and mass transfer. The first question asks you to create the steady-state one-dimensional heat conduction equation for a long cylinder. In order to do this, you're going to start off with the generic heat equations, with E being the energy for that element, which is the tube. And then from there, you're going to simplify to make sure that you set your energy equal to mc delta T, which is the two T's related from T now and T plus delta T, as in a time a little bit from now. And then next, you're going to make a few substitutions. The first substitution is that you set the area equal to 2 pi RL and you divide by that, and that's going to give you this formula down here. And then from there, you're going to take the limit as delta R and delta T go to 0. And basically, since these are the definition of a derivative, it's going to come out to dt over R and dt over dt. And then from there, because of Fourier's law, you're going to come out with the final answer right here. The next problem I'm going to go over is 2-66. This you have heat being conducted, transferred through a surface into water that's in an insulated surface. In order to do this, you're going to start out with the fundamental Cartesian one-dimensional flow, and you're going to set that equal to 0, and then you're going to integrate it twice, and that's going to give you this formula, the two coefficients of integration. And then you're going to apply two boundary conditions, the first one being no heat flux at the interface, and then the second one is that there's going to be no temperature difference between the surrounding temperature and the surface of the conducting material. And from there, you're going to get your two integration coefficients, and then you're going to solve for the net heat flux. And from there, you're going to use the Q absorbed by the conducting material from the sun, subtracted the Q radiated by the material, subtracted by the Q conduction material. And you're going to use the formulas for that, and that's going to give you this answer. And then for the next one, you have a wire that is emitting heat in a water surface. In order to do this problem, you're going to start off with the fundamental equation for one-dimensional radial flow with a steady state. That's why there's no time dependency. And then from there, you're going to apply two boundary conditions. The first one being that the convective interface between the outside of the wire and the water surrounding it. And the second, that there's going to be no flux at the center point of the wire. This is due to symmetry. And there you're going to solve for the two coefficients of integration. And then from there, you're simply going to apply those, and then you're going to solve for the temperature at 0 by replacing the R's with zeros, and that's going to give you this final answer. For the final problem, it's asking you to do a few things. The first thing is that you're in a relative humidity of 100%, meaning the air is saturated, and it wants you to find the mole fraction of the water vapor in the air. In order to do that, you're going to use the Raoult's law. However, you're going to make one assumption that the mole fraction of liquid water is basically 1. That's because there's not much air actually is soluble into the water. And from there, you can simplify that down into xi equals 1, and then you can get your mole fraction of water in the air. And then next, I want you to find the mole fraction of the air in the liquid. In order to do that, we're going to use Henry's coefficient. And again, we're going to assume that there's almost no gas in the water, therefore we can use Henry's coefficient. Alright, from there you're simply just going to solve for the y air, and that'll give you your answer. Thank you.